Gain boosting, the limited gain of the single-stage op-amp studied in session and the difficulties in using two-stage op-amps at high speeds have motivated extensive work on new topologies. Recall that in one-stage op-amps such as telephonic and folded cascade topologies, the objective is to maximize the output impedance so as to attain a high voltage gain. The idea behind gain boosting is to further increase the output impedance without adding more cascade devices. Here you can see the figure increasing the output impedance by feedback. Consider the simple cascade in figure A whose output impedance is given by Rout is equal to GM2 R0 to R01 as far as Rout is concerned. M1 operates as a degeneration resistor, figure B, sensing the output current and converting it to a voltage. The observation that the small signal voltage produced across R01 is proportional to the output current suggests that this voltage can be subtracted from VB so as to place M2 in current voltage feedback, thereby increasing the output impedance illustrated in figure C. The idea is to drive the gate of M2 by an amplifier that forces Vx to be equal to Vb. Thus, voltage variations at the drain of M2 now affect Vx to a lesser extent because A1 regulates this voltage. With smaller variations at X, the current through R01 and hence the output current remain more constant than those in figure B, yielding a higher output impedance. The reader can prove that Rout similar to A1, GM2, R02, R01. Concluding that Rout can be boosted substantially without stacking more cascade devices on top of M2. Since for small signal operation VB is set to 0, the circuit can be simplified as shown in figure A, with the amplifier possibly implemented as in figure B, called a regulated cascade. The overall stage is illustrated in figure C, exhibiting a gain equal to mod AV similar to GM1, GM2, R02, R01, GM3, R03, similar to the gain of the triple cascade. This topology was first invented in 1960 and 1974 and applied to boost the gain of op-amps in 1989. Here you can see in this figure gain boosting in cascade stage. Before incorporating the technique of figure C in an op-amp, let us examine the output voltage swings in particular. The minimum allowable level since Vx is equal to Vgs3, the minimum value of Vout is VOD2 plus VGS3, whereas in simple cascade with proper choice of VG2 it would be VOD2 plus VOD1. Thus the auxiliary amplifier in this case limits the output swing. Now if we now apply the gain boosting to a differential cascade stage such as shown in figure A, since the signals at node X and Y are differential, we summarize that the two single-ended gain boosting amplifiers A1 and A2 can be replaced by a one differential amplifier. Figure B. Following the topology of figure C, we implement the differential auxiliary amplifier as shown in figure C, but nothing that the minimum level at the drain of M3 is equals to VOD3 plus VGS5 plus V1SS2, where V1SS2 denotes the voltage required across ISS2 in a simple differential cascade. On the other hand, the minimum would be approximately one threshold voltage lower. The voltage swing limitation in figure C results from the fact that the gain boosting amplifier incorporates an NMOS differential pair. If nodes S and Y are sensed by a PMOS pair, the minimum value of Vx and Vy is not depicted as the by the gain boosting amplifier. Now here you can see in this figure boosting the output impedance of a differential cascade stage. Here you can see in this figure folded cascade circuit used as auxiliary amplifier. Recall from session that the minimum input CM level of a folded cascade stage using a PMOS input pair can be 0. Thus, we employ such a topology for the gain boosting amplifier arriving at the circuit shown in figure. Here, the minimum allowable level of Vx and Vy is given by VOD12 plus VVISS1. Regulated cascades can be utilized in the load current sources of a circuit op-amp shown in figure A. Such a topology boosts the output impedance of the PMOS current sources as well, here thereby achieving a very high voltage gain. To allow maximum swings at the output amplifier, A2 must employ an NMOS input differential pair. Similarly, similar ideas apply to folded cascade op-amps. Figure B. Here you can see in this figure gain boosting applied to both signal path and load devices. Now recall that the premise behind gain boosting is to increase the gain without adding a second stage and more cascade devices. Does this mean that the op-amp of figure have one stage nature? After all, the gain boosting amplifier introduces its own poles in contrast to two-stage op-amps where the entire signal experiences the poles associated with each stage. In a gain boosted op-amp, most of the signal directly flows through the cascade devices to the output. Only a small error component is processed by the gain boosting amplifier and slowed down. Thank you.